It's fabulous to have the second keynote of our summit today. We're extremely delighted to have Virginia Smith. She is an assistant professor at CMU who investigates a wide variety of machine learning and system-related topics. She examines things like core issues like optimization, distributed systems, large-scale machine learning, and of course, federated learning is one of her key areas of interest. Prior to joining CMU, she was a postdoc with Chris Ray in Stanford University, and prior to that, she completed her PhD at Berkeley, working with Michael Jordan and David Culler. She also has won a number of awards during her academic life. For example, winning the Google Research Scholar Award twice, the Facebook Faculty Research Award back in 2020. And she's one of these key scientists who helped spearhead the creation and ongoing support of the Machine Learning and Systems Conference, MLSys. And she served as PC chair for MLSys in 2018. I believe. And so with that introduction, she is here today to speak to us about issues of heterogeneity and how this interacts with communication efficiency in the realm of federated learning. And so we are delighted to have her. Thanks for joining us, Virginia. If you want to perhaps turn on your camera and share the screen, we can begin. Thank you for being here.
Sure, absolutely. Thank you for having me, and thanks so much for the introduction. So let me go ahead and share my screen and make sure you all can see that okay.
And we'll run the session similar to the other ones where people can type in questions in the chat and we'll collect them at the end, and then we'll pose them to you once you're done. So yeah, thank you very much.
Okay, that sounds great. Yeah, so thanks again for having me. As Nick mentioned, so my name's Virginia Smith. I'm a professor at Carnegie Mellon University. And today I'll be talking about some of my work in federated learning that specifically looks at the issue of heterogeneity. And we'll see various ways that heterogeneity may affect the entire machine learning pipeline in federated settings. Okay, so just to start with some motivation, I'm sure that many of you are all familiar with the problem of federated learning, but just to give it a concrete definition for the purpose of this talk. Specifically, I'll be looking at federated learning with the goal of training machine learning models at the edge. So why would we do this? Why do we care about this problem of federated learning? Well, if you compare it to something like traditional cloud-based training, where you may have a large number of devices that are generating data, but you don't actually process that data at the edge. You send all of that raw data back to the cloud where you perform training and then maybe send the model or the predictions back to the device. In federated learning, the goal is really to push as much of that computation to the edge as possible. And so you're performing the training in a distributed fashion over the edge devices. This can be useful to allow you to more quickly incorporate new data that you're seeing. It also helps to reduce strain on the network. So by not sending all of that raw data that you're receiving from these devices, you can really help to improve the overall communication efficiency of these systems. And there can also be some privacy benefits to keeping that raw data local, as opposed to moving that all to some other location. Okay, just as a kind of a high-level explanation of the typical workflow in federated learning, and specifically talking about the way that federated learning differs from prior work in distributed learning. Let me give this kind of canonical example of the federated learning workflow. So typically in federated learning, the goal is to solve some machine learning objective. So this might be something like what I'm showing here, like an empirical risk minimization objective, where the goal is to find one model that's a good fit for all of the data that's distributed across the federated network. So the objective might look like this. We're basically trying to sum across our n devices a set of losses, where the loss is basically just ensuring that the model W is a good fit to the local data on each of the devices K. Okay, and how does training happen if we're trying to solve this objective now in a distributed fashion over these n devices? At a high level, what can be done is that you may have some central coordinator that's helping with this training process, that's storing the model updates. And at every communication round, the server sends the current notion of the model to a subset of the devices, which perform some local training and then send their model updates back to the server, where they are aggregated and used to form the next model iterate. Okay, so this high-level workflow for this distributed training regime sounds a lot like prior work that's been looked at in, say, the data center setting, where the goal is to perform, to solve this machine learning objective across a distributed set of machines. But there are a few really critical ways that this setting differs from prior work in distributed learning. So one is that if you're imagining this being a large network of devices, such as mobile phones or wearable devices, communication is known to be a bottleneck, even in the data center setting. But here it can be a really, really massive bottleneck. So you might have very, very large networks of, instead of just hundreds to thousands of machines, you might have thousands to millions of devices. And the networks themselves can also be slow. So if you think of something like a mobile phone network, it could be that the network connections are also much slower. They can also be unreliable, right? So you might have devices in the network that have poor network connection, or you might have practical issues like someone turning their phone off. And this results in this communication being not only very expensive, but also sometimes quite unreliable. Okay. Additionally, as I mentioned, there can be some important privacy motivations that inspire the use of federated learning, right? So, one of the ideas in federated learning is that we can potentially get some benefits by keeping the raw data local on these devices, but there are still privacy concerns with sharing any information over the network, right? So we have to think about how we can additionally make some of the updates that we're sending private to ensure that we can still satisfy user privacy constraints for federated learning applications. Okay, and this is something that really might differ from work, say, in the data center setting, where typically you assume that some cloud provider, say, owns and can operate across all of the data on all of the machines. Okay. Finally, another way that this setting really differs from something like the data center setting is because all of the data is being generated on these devices, and you're also processing it on these devices. So you're not moving or repartitioning the data in any way. There can be a lot of heterogeneity in the data. So this can be of the form just that some devices might have much more data than others, so the data can be unbalanced, but can also be non-identically distributed. So some data on some devices might look very different than data that's been generated on other devices. Okay, and as we'll see in the talk today, this issue of heterogeneity, in fact, can affect multiple aspects of the machine learning pipeline. Okay, and finally here, I wanted to note, related to heterogeneity, that heterogeneity can come in the form not just of the data, but also in terms of the underlying compute substrate. So the devices, for example, might have variable hardware or connectivity, and all of these aspects of the systems related issues with the devices can really affect how capable each of these devices are at participating in this training procedure at every round. Okay. I wanted to note here that if you are interested in learning more about some of these challenges and current approaches and future directions, I wanted to just point out two recent resources that I've been grateful to be involved in. So one is a white paper that we wrote last year defining specifically some of these challenges and current approaches and future directions. And another, which is maybe a little bit more user-friendly, is also a tutorial from NeurIPS this year, where we talked about some of the challenges that exist in federated learning as well as federated analytics. Okay. For the remainder of this talk, though, now all of these issues are quite important in the federated setting. So I'm going to be talking again about privacy and communication. But the key issues I'll be focusing on really are these issues of heterogeneity. And we'll see how, specifically when we're thinking about the interplay also with these other challenges, these become a really big issue and an area of open research when thinking about how to tackle the problem of federated learning. Okay, so what do I mean by that? In what ways can heterogeneity either from the data or from the underlying systems, affect the machine learning pipeline in federated settings. So we'll be looking at answering multiple questions today. So one of the first questions, this may be one of the questions that first comes to mind when thinking about the possible effects of heterogeneity, is trying to understand how heterogeneity may affect the training procedure. So specifically, how does heterogeneity affect the optimization methods that we use to solve the machine learning optimization objective in federated networks? Okay, but it turns out that the effect of heterogeneity doesn't just stop with the optimization method. It can also affect how well the model that we learn performs across the network. And in particular, if you have data that looks very different on some of the devices, it can happen that the model that you learn performs very well on some of the devices, on some subsets of the data, but very poorly on other subsets of the data. And for this reason, to deliver a reasonable quality of service across your federated network, it can be important to think about how to equalize the performance of the model that you're learning. Okay, and finally, this question of how can we best understand the performance of the model really goes down to how should we actually be modeling federated data, especially data that might be heterogeneous. And this is really a question maybe at the top of the stack of this machine learning pipeline. What is the modeling approach that we should be using in this setting? And in particular, how can we develop models that are personalized to the unique and potentially diverse data that's coming from each of the devices? And so if you think about these questions, they roughly bucket into thinking about how heterogeneity affects the optimization procedure, how it affects this notion of fairness, where we want the model to perform reasonably well across all of the devices, and how fundamentally should we think about modeling data that's been generated in federated networks. So I'll talk a little bit about each of these problems. And as I do, I'll point out on the bottom part of the screen here, some of the collaborators that I've worked on. So I've been very fortunate to work with a great number of collaborators on these problems. And I'll try to note that in the corner of the screen. Okay, so let me start by talking about this problem of optimization. So optimization is really the critical part of actually performing this training, right? So we have to use an optimization method to solve our machine learning optimization objective, right? So how can we do that? What are some of the methods that are commonly used to solve this machine learning objective in federated settings? Okay, and one of the most commonly used methods for optimization in federated networks is a method known as federated averaging. So this method has become particularly popular because it's very efficient in terms of communication. So it really helps to reduce the communication bottleneck in massive federated networks. And it's actually a very simple method. So basically what happens is at each communication round, a central coordinator sends the current model iterate to a subset of the devices. This is just like the diagram I showed on the previous slide. Then these devices that are selected perform some local training. Specifically in federated averaging, they perform epochs of mini-batch stochastic gradient descent locally. Then these devices send their model updates back to the central server where they are averaged, as noted in the name federated averaging. Okay, so why is this method so popular? One, it's quite simple. Two, it works remarkably well in practice, especially for deep neural networks, which are commonly used in federated learning applications, and especially when you care about this issue of communication. So performing this local training can really help to reduce the total number of communication rounds that you have to run this method for. Okay, but what can go wrong? So it turns out that even though this method works quite well in practice, it can also work quite poorly in some regimes, specifically when the data is heterogeneous. So when you have certain devices that generate data that looks different from other devices, when the data is non-identically distributed, in fact, this method, federated averaging, can exhibit some really poor convergence behavior. Okay, so let me show you what I mean by that. So if you look at this method, federated averaging, and you look at the performance of federated averaging on actually a very popular federated benchmark. This is a Shakespeare benchmark where the goal is to perform some next word prediction across a bunch of text from Shakespeare's plays. Okay, so this is a data set that's trying to represent what you might naturally see in a network where you're trying to perform, say, some text prediction across a set of mobile phones. Okay, and if you look at the performance of federated averaging in this naturally heterogeneous data set, what you see is that in terms of the number of communication rounds to reduce the training loss, so you want to get down to the bottom of this plot as quickly as possible, what happens is that as you do more local computation, as you increase the number of local epochs that you're running mini-batch SGD for, you start to see this unfortunate behavior, which is that you want to, increase the amount of local computation to help reduce communication. But as you increase the amount of local computation you're doing, you start to see that you're converging to a worse solution. You're converging to a solution with higher training loss, and training loss is what we want to minimize. Okay, and I wanted to note here that this the main issue here is that if you're running federated averaging, basically you can have this issue that doing too much local work can hurt the convergence behavior when you have heterogeneous data. Okay, and it turns out that this can get even worse when you also think about the fact that there may be heterogeneity from the underlying devices themselves in terms of their systems capabilities, right? And so the way that this can manifest itself in federated networks is that if you have some devices that have different hardware capabilities or different network connection than other devices, it may be that you have issues with stragglers, right? So you have some devices that might take a very, very long time to perform their local computation, or may just drop out of the training round at any one communication round that you have. Okay, and a common way to deal with this in federated learning is basically just if you have a device that's performing its update, but it's running very slow, you can just drop the information from that device. So you can say, this device has not completed its local computation, so I'm just going to ignore the information from that device. Okay, and it turns out that when you do this, this can really exacerbate issues that already exist because of statistical heterogeneity. So if you end up having, say, a large number, this is an extreme case where we have, we're looking at 90% of the devices being stragglers. But if you have some stragglers in the system, this can really amplify some of the issues that already exist because of statistical heterogeneity. Okay, so the key punchline here is that, the issue of systems heterogeneity, which often results in stragglers or maybe dropping devices, can really exacerbate convergence issues that already exist for methods like federated averaging. Okay, so how can we deal with this? Are there any ways that we can address this issue of heterogeneity in terms of the optimization procedure? And a simple approach that we've taken in recent work is to look at an alternative to federated averaging, where we make the following simple modification. Basically, our intuition is that if the issue is that the federated averaging procedure starts to exhibit worse convergence behavior when you do too much local work in heterogeneous settings, we can try to find a way to modify the subproblem that's solved in federated averaging to prevent this method from doing too much local work, and specifically to relate the amount of local work that should be done to the degree of heterogeneity in the network. Okay, so we introduced the following modified local subproblem, where basically what we're doing is we're adding this proximal term to the original objective. And what this proximal term does is it limits the amount of deviation that you can have in your model update from the previous model iterate. So it helps to prevent you from doing too much local work. Okay, so this proximal term at a high level, what it's doing is it's limiting the impact of local updates. And then additionally, one nice benefit of this proximal term is that it can allow us to safely incorporate partial work from different devices. So specifically, because we're using this term that limits how far each of the devices may be making updates, we can allow for different devices to perform variable amounts of local updates. So if you have some devices that are running more slowly, you have stragglers, rather than just dropping the information from those devices, we can just take whatever approximate solution those devices have generated in a given time window. Okay, so these are the two main updates that we make in the FedProx framework. So we try to address statistical heterogeneity through this proximal term and systems heterogeneity by incorporating partial work from the devices. Okay, another benefit to this approach is that we can provably show that this method converges. And specifically, we can relate the convergence of this method to the degree of heterogeneity in the network. So I'm not going to go into too many details here, but I wanted to show you just a high-level overview of what those convergence guarantees look like. So basically what's being done is that we can show provably that this method FedProx converges, despite the fact that the data might be non-identically distributed across the network, despite the fact that we're in this kind of more challenging setting to analyze where we're performing local updating, and there might be partial or variable participation from the devices. And how are we doing this? Specifically, what we do is we assume that we have some understanding of the notion of heterogeneity in the network. And we characterize the heterogeneity via this term here. And basically what this term is doing is trying to understand how much the data varies across the network. So this term B will be larger if the amount of heterogeneity is larger. Okay, and we can relate this issue of heterogeneity to our convergence behavior. So specifically, going back to the previous slide, what you will see is that our convergence depends on this mu term. So specifically, what we'll have is that if you have a larger value of B here, meaning that you have more statistical heterogeneity, you will need to set that parameter mu to be larger in order to guarantee convergence. Right, so this gives you a nice way to rigorously trade off how you should think about trading off local work versus heterogeneity in realistic federated networks. Okay, I wanted to note here that the benefits aren't just in terms of the theoretical behavior. We also have shown that this simple modification of adding this proximal term to the objective also really helps to improve the performance in practice. So for example, if you look back at this Shakespeare data set that I talked about, and we're looking at this very difficult regime where we have a tremendous amount of systems heterogeneity and statistical heterogeneity. First, the first kind of key takeaway from FedProx is that we can get some benefits just from not dropping devices in the setting where we have systems heterogeneity. So rather than dropping information from devices that are performing very slowly, we can just take the partial updates that have been performed on those devices. And then the benefit of FedProx is that we can, by tuning this parameter mu to address that heterogeneity, we can ensure that the method can converge and can converge with some, kind of nice theoretically grounded behavior, right? So we can see, in fact, across a suite of federated data sets that this FedProx framework has two concrete benefits. One, allowing for partial work in the setting where you have systems heterogeneity can really benefit convergence. But two, forgetting about whether or not you have systems heterogeneity, using FedProx with this mu parameter, which we can tune, really helps to improve the stability of the method and allow it to converge to the correct solution. Okay, so this allows you kind of both benefits of being able to use the communication efficient and kind of commonly used federated averaging method, but to do so in a principled way that still allows you to converge to the correct solution. Okay, just to give one kind of statistic or takeaway across the wide set of data sets that we looked at, we were able to achieve a 22% absolute test accuracy improvement on average across those data sets. So this translates not only to improvements in terms of the convergence behavior on the training objective, but also to concrete improvements in terms of the test performance. Okay, so let me stop here with just some takeaways in terms of the optimization section, and I'll try to save some time at the end of the talk in case there were any questions about the material that I presented. But the high-level takeaway in terms of just this first part on optimization is basically that how does heterogeneity affect optimization methods? It can lead to slower convergence, it can reduce the stability of the optimization method, and it can even lead to divergence. Okay, and for this reason, it's really critical to understand and analyze and develop federated methods with these practical assumptions in mind. So thinking about the fact that the data might be non-identically distributed and that there might be partial or variable participation from the devices depending on their underlying systems characteristics. Okay, so we've seen that has a big impact on the overall optimization performance. Okay, so as I noted, though, the issues with heterogeneity don't just stop with the optimization method itself and understanding the convergence of these methods. There are also important issues stemming from heterogeneity that we have to think about when thinking about evaluating how well the model that we've trained performs in federated networks, especially when we have heterogeneous data. Okay, and so what do I mean by that? So I mentioned previously that one of the most common objectives that we think about solving in federated learning would be these, traditional empirical risk minimization objectives. Basically, these are of the form that we're trying to minimize a set of losses across the n devices in the network. So each of these functions, f1 through fn, could represent a set of local losses on each of the n devices, right? And the goal of these losses is just to ensure that the model that we're training is a good fit to the data that's being generated by these devices. Okay, one issue though is that when we think about solving this empirical risk minimization objective, we typically think about just minimizing a sum or an average of the losses across the n devices. Okay, and why can this be an issue? What this will do is it will ensure that your model performs well on average, but there's no real guarantee for the accuracy on the individual devices. So in particular, you might do very well on average, but while having very variable performance across the network, right? You might do very well on average, but by performing quite well on some devices and quite poorly on other devices. So you can have a lot of variability in terms of the performance of the model. Okay, and just to give an example of this, this is from the previous data set that we looked at, Shakespeare. And this is an example of just training an ERM objective on this application. And what you can see, this is a histogram of the test accuracy distribution across the devices when training a model just using a traditional ERM objective. What you can see is that on average, you perform quite well by training this objective, right? So on average, the accuracy on most of the devices is quite high, but there are a few devices where the accuracy is quite low, right? And so this is the sort of behavior that we want to prevent in realistic federated networks, right? We want to do well on average, but we don't want to have this case where our model exhibits some kind of catastrophic, accuracy performance, right? We want to ensure a reasonable quality of service for our model across all of the devices in the network. Okay, and so this is the question that we asked ourselves in this recent work is, are there ways to encourage a more fair or uniform distribution of the model performance across devices? Okay, and in thinking about how to solve this problem, we were actually inspired by some previous work in wireless sensor networks, which is thinking about a very similar problem of how can you fairly share some resource like bandwidth across a distributed network. And the analogy to draw this into this machine learning objective is that the resource that we're sharing in machine learning are these losses, right? So the larger the loss on a given device, the more effort your model will put into fitting to that local data. Okay, so with this in mind, we drew inspiration from this alpha fairness framework, which has been developed for issues of resource allocation in wireless sensor networks. And using this objective, but now on this machine learning objective, we can define the following variant, which we're calling Q-fair federated learning. Basically, what's being done is that you're taking each of the losses and raising them to some exponent Q. And the effect of this will be the following. The larger that you set Q, the more that this objective will amplify large losses. In the extreme, when Q is set towards infinity, what this will do is force you to minimize the worst performance on any one of the devices. Okay, so you can think about this. One thing that's nice about this objective, though, is you can think about this as a tunable framework. So depending on how you set Q, if Q is 0, this just defaults back to the ERM objective that we showed in the previous slide. As Q goes closer and closer to infinity, you get this specific notion of fairness that's been looked at in the federated setting as well as in just traditional machine learning, where you want to minimize the worst performing device. Okay, and in this work, we specifically look at understanding this objective, analyzing the effect of changing Q. So how does that affect the guarantees that we have on the model that we've trained in these networks? But we can also show that it works quite well in practice. So if we go back to this previous example, by using this Q-fair federated learning objective, we can actually perform just as well on average, but by increasing the performance of these worst performing devices, right? So how are we doing that? Of course, it doesn't come for free. What you can see is that we're performing a little bit worse on the best performing devices, But now we've significantly improved these worst performing devices. Okay, and we've shown this across a wide suite of federated benchmarks, that basically what you're able to do, this is just kind of one takeaway from these experiments. I realize it's a lot to look at these plots, but basically on average, we can show that you can cut the variance of the accuracy distribution in half while maintaining the exact same average accuracy. So you can perform just as well on average as you were previously, but you're preventing these issues of catastrophic failure kind of at the edges here. So you're really cutting the variance of the accuracy distribution. Okay. I wanted to note also that this objective actually has many more applications beyond just the specific application in federated learning. I'm not going to mention too much here, but if this objective reminded you of anything else, or if you're interested in some of the other applications, this is something that we've looked at more generally in some recent work. We've generalized this objective to also consider values of Q that are negative. And we've looked at a bunch of possible applications of this objective for things like handling fairness and class imbalance and dealing with outliers. So actually this objective is very broad, and there's a lot of interesting properties and connections to prior work with this objective. Okay, so let me kind of just finish here, what the takeaways are in terms of thinking about evaluating the performance and ensuring fair performance in federated networks. The main takeaway here is that if you aren't careful, if you're just solving, say with just the vanilla ERM objective, and you're solving this objective in a heterogeneous federated network, it may be that, vanilla ERM can deliver good performance on average, but poor quality of service across heterogeneous devices. Right? And for that reason, it can be useful to think about objectives like the one I discussed today, Q-fair federated learning, that allow for a flexible trade-off between fairness and accuracy. Okay, so the last part of the talk today, and then I'll stop in case there are any questions. And this kind of goes back to the highest point in the stack. How should we really, what modeling approaches should we really be using to model federated data? And in particular, if we know that the data is coming from different distributions, how can we develop models that are personalized to the unique heterogeneous data on each of the devices? Okay, so this is a question that we asked ourselves actually in work several years ago. What is the best way to really think about modeling federated data? On one extreme, if you have, say, a network of devices here, and I'm drawing these devices to different scales to represent the fact that they may be generating different amounts of data or different looking data. One extreme is that you can just solve a separate model for each of the local data sets, right? So this is maybe the first thing that you would think about doing. Now, these models are, of course, very personalized to the local data, but the downside here, and the reason that we're excited about federated learning, is that there can be some benefits for sharing this data, right? Potentially some of the problems that some of these devices are facing are similar to the problems that the other devices are trying to solve as well. And for that reason, we may want to be able to learn from peers in the network. Okay, and so this is one of the goals of federated learning, is to share data, especially when some of the devices here might be generating an insufficient amount of data or an insufficient quality of data. It can really be helpful to think about how to gather all of this data at once in a federated fashion to train this one model. Okay, so this is the de facto approach in federated learning, is to train just one model across all of your federated data. So this, of course, allows you to learn from peers in the network. It can really boost the effective sample size of each of the devices' data. But the issue is that if the data truly looks different across these devices, even just minor differences, we're not necessarily able to pick that up by learning just a single global model. Okay, so what we were really looking for as an alternative to these two extremes is something in between. Intuitively, we wanted to develop models that were personalized to the heterogeneous data on these devices, but we also wanted to share data in an informed way. So we want to be able to learn from peers in the network, specifically peers that are generating data that look like data on other devices. Okay, and in tackling this problem, we looked specifically at prior work in multitask learning. So multitask learning is a very natural fit for this problem of federated learning with heterogeneous data. Specifically, what multitask learning does, the idea is that you learn a separate model for each of the devices T. So each of these devices T is generating some data X sub Ti, and we're fitting losses just like we had previously. So we're learning some separate models for each of the devices. But then crucially, we're also learning about the structure that exists between those devices. And we're learning about this structure through this regularization parameter. Basically, what this regularization parameter does is it takes all of these models into this matrix W, and it learns about the relationship between the different models, between the different tasks in this multitask learning objective. And this regularizer, this is very abstract here, but this can encompass many different possible types of relationships. So you might learn, for example, that all of the devices or tasks are related. And what you're learning is just the weights on the edges in this connected graph. Or you might learn that there are outlier devices. So some devices that are very unrelated to the other devices. Or there might be clusters or groups that form in your network. You might have clusters of devices that are very similar to one another. Or there may be some asymmetric relationship. There might be some device that's performing, most of the interesting, that's gathering most of the interesting information in the network. Okay, so this is a very, very general framework. And this multitask objective in particular makes a lot of sense when you're trying to model heterogeneous data. Okay, and crucially, I wanted to note here that you don't have to know these relationships beforehand. You can learn them directly from the data itself. So you don't have to kind of encode this information beforehand. This is something you can learn as part of the machine learning process. Okay, so this is something that, as I mentioned, we had looked at several years ago, actually, and have shown that multitask learning is quite effective in federated networks, especially networks where the data is heterogeneous. This can really help to boost the accuracy of the models that you're learning in these networks. But there were a couple issues with the initial objective that we looked at in looking at federated multitask learning. So one issue is that when you're learning this task relationship matrix, this involves learning a matrix of size M by M, where M is the total number of devices. And if we're thinking back to some of these examples, say of learning in a network of mobile phones, where there might be millions of devices, learning this entire task relationship matrix can really become quite prohibitive. Okay, so in order to think about how we can perform multitask learning in a more scalable fashion, we've looked recently at an alternative to the general framework I presented on the previous slide. Where basically we're doing exactly what we had previously, where we're learning separate models, one for each device. But then we have a very, very simple form of multitask learning, where basically all we're doing is we're ensuring that each of these local models doesn't deviate too much from the global model, the model that's trained across all of the data in unison. Okay, so you can think about this as a simple form of multitask learning, where we ensure that the personalized models that are trained on each of the local devices are close to the global model. Okay, to solve this, and another way to think about what this objective is doing, you can basically alternate between fitting a global model just as you would normally in federated learning, and then performing some local fine-tuning to learn this personalized model, WK. Okay, this is in fact not just quite a scalable method, but there are also some other benefits to this multitask objective. So because you're basically just doing this procedure of fitting the global model and then fine-tuning, this preserves the privacy and communication benefits that you have in traditional federated learning. So this can be a very scalable and practical way to provide multitask learning in federated networks. Okay, but one thing that's quite interesting in looking at this objective and analyzing the performance of this objective, both in theory and in practice, is that we've been able to show that there are benefits of personalization that go beyond just accuracy. So we've already shown previously, and I'm showing in this plot here as well, that multitask learning, basically the green bar here, can improve test accuracy. And even this very simple form of multitask learning that I showed on the previous slide, across the boards can kind of beat these simple baselines of learning just a global or learning just a local model in federated settings. But it turns out that there are also other benefits of personalization as well. So in particular, because you're learning separate models for each of the devices, there can be some nice robustness benefits of personalization as well. What can happen is that if you have some devices that become corrupted or are generating data that looks different from the other devices, noisy data, perhaps adversarial data. By using this multitask objective, you can help to reduce the emphasis that you put on just learning this one single global model. So this also helps to reduce the effect that these adversaries can have when you're learning just a single model, right? So by performing personalization, what you can in fact see is that you can potentially learn separate models for the clean data and the corrupted data. And this is something that we've looked at in recent work. Even with this very simple multitask learning objective, we're actually able to show that we can perform significantly better than common robust baselines like, say, multi-crum, for example, which is commonly used to enforce robustness. What you can see is just by using multitask learning, when you have a large number of malicious devices, you can retain the same accuracy essentially that you had on the benign devices. Okay, so this is just by using multitask learning, there are inherent benefits to delivering robust performance. Okay, and these benefits also relate to issues of fairness, similar to what I talked about previously. So what you can see is that in terms of minimizing the variance in the accuracy distribution, these multitask learning objectives also deliver you highly fair models. So they really help to reduce the variance of the performance, right? And the way that they're doing that is because they're allowing you to learn separate models for each of the devices. So if we look at comparing this multitask objective to common fair objectives like the QFFL objective I presented earlier, just by using multitask learning, inherently you get all these fairness benefits without using the more sophisticated fair objective that I presented previously. Okay, and there's one other point here, and I think this relates also maybe to some of the points from the other keynote today, which is that one issue in federated learning is that some of the robust baselines that we typically think about, like say using the median, what the median does is it helps to get rid of the tail behavior. This is a great thing to do if that tail behavior is coming from an adversarial device. But if that tail behavior is just because those devices are generating different data than other devices, you can get this behavior that the robust methods that you use are not delivering fair performance. Okay, and similarly, if you're using a fair method like the QFFL objective that I presented earlier, you're going to be amplifying the performance of the worst performing devices. This can also have this unfortunate behavior that you might be amplifying the performance of adversarial devices. Okay, so what using multitask learning and personalization allows you to do is really get rid of this tension between fairness and robustness and to achieve both of them simultaneously. And so if you're interested, this is a recent work at ICML. We looked at these various constraints and we looked at this simple multitask learning objective and have analyzed and demonstrated the ability of personalization to deliver not only accurate models in federated settings, but also robust and fair models, which are really important considerations when you have heterogeneous networks. Okay, I'm going to skip that slide in the interest of time. So I just wanted to summarize here, and then hopefully we can save the last couple minutes for questions. The main idea here in terms of modeling is that when you have heterogeneous data, it can be important to think about how to personalize the model that you're learning in a federated network. Multitask learning is a principled way to learn personalized shared models. And this has benefits not only in terms of accuracy, but in terms of other constraints like robustness and fairness, which are common concerns in federated settings. Okay, what's next? I wanted to just end on one final slide here and maybe kind of end with a positive note. One thing I wanted to mention is that a key problem in really understanding heterogeneity is not only analyzing the effect of these methods and models in terms of possible heterogeneity, but really having a good grasp on what heterogeneity looks like in real federated networks. And so, if you're interested in collaborating along these lines, I think it's really critical to have a good set of open source data sets from organizations that are using federated learning in practice. And so if you'd be interested in collaborating along these lines, please do reach out. Finally, just to end again on a positive note, I wanted to note that today I've talked about a lot of the potential pitfalls of learning in heterogeneous networks. It can affect optimization methods. It can affect the convergence of these optimization methods. It can affect how we evaluate the performance of the model that we're training. And it can also impact the model that we should be learning in the first place, right? It can necessitate using personalized models. Okay, but in fact, there may also be some interesting benefits of heterogeneity. And this is something that we've looked at in some recent work. So one example where having heterogeneous data can actually give you some benefits is in looking at a problem like clustering. So if you want to perform clustering, basically what you want to do is you want to take all of your data and understand different clusters that exist in the underlying data. Okay, and the intuition is that if you're in a federated network where the data may already be sort of forming these clusters according to which device the data is being generated by, there can be some real benefits for performing clustering in this setting relative to the baseline of, if you had just taken all of that data and partitioned it in an IID fashion. So specifically, something that we've looked at in recent work is developing an efficient one-shot clustering technique. So basically, you perform local clustering on each of the devices, you communicate that information once, so there's only one communication round, it's very, very efficient, and then you cluster at a central location. And what we can show is that heterogeneity in this setting provably leads to stronger guarantees in terms of clustering. So it delivers better clustering performance. And why do we care about clustering for federated learning? Why would we care about this application? So clustering, there have been numerous applications of clustering recently in the federated learning literature. So this can help to improve how you should sample clients or devices at every round. And there can also be benefits in terms of thinking about personalization, right? So you can learn personalized models for different clusters in the network. Okay, this is just a sample of the results there. But if you're interested in this work, again, just to end on more of a positive note here, there can be some interesting benefits of learning across heterogeneous networks as well. Okay, thanks. That's all I had. I think we have maybe just a few minutes for questions, but I'd be happy to answer questions if there are any.
Thanks so much. That was a great talk. I'll clap for on behalf of everyone who's listening. So yeah, thank you very much, Virginia. We do have a couple of minutes. I'll sort of scan through the questions that were asked. Perhaps we'll start with a practical question. One of the questions was, how do you recommend handling optimizer state on the client side? Do you reset it it is reset every time the client gets selected. After all, the optimizer state does not match the global model parameters anymore, but it also means that the optimizer would be starting from zero for things like momentum and so on. So any thoughts on this very practical sort of issue?
Yeah, that's a really good question. So I should say, so I guess the baseline would be to assume that you maintain no state. So this is kind of the assumption that we work off in a lot of our experiments. For example, the FedProx framework that we have analyzed, the assumption is just that you start from the previous model iterate, which is sent to you from the central server at each communication round. But I think it's a great question of, especially if you're thinking about performing things like federated hyperparameter tuning, how can you leverage the fact that you have seen this, you've been performing training previously, how can you leverage that across federated networks? So this is something that we've actually looked at recently in some work on hyperparameter tuning in federated settings. Actually through a connection to neural architecture search. There's a very common approach there called weight sharing, where basically the goal is to share things like weights, or in this case, things like hyperparameters across the network. And so it's an interesting, it's a very, very difficult challenge. I think I would say that at a high level, tuning the hyperparameters is a critical but very challenging problem in federated learning. And this is one interesting, technique that we've looked at recently. But I think there's still a lot of open work there to think about how to do this.
I mean, I like the idea of borrowing that weight sharing idea from NAS to see if it would sort of help things in a file setting. Cool. Okay. So I guess another to address another question that was posed. The question was. The person writes, I was wondering if you see asynchronous model updates as a viable avenue in federated learning, i.e. stragglers sending updates for a previous global model state, I guess, as a mechanism. What are your thoughts as that as an approach?
Yeah, so I think, let me answer very broadly at first. I think there's obviously two common approaches. There's the asynchronous approach where you perform some model training and then you send those updates immediately. And then there's the synchronous approach. In federated learning, one of the benefits of the synchronous approach is just that it lends itself more naturally to some of the privacy and security mechanisms that are being used in federated learning, where you have to kind of aggregate all of the information at once. But I think it's much more natural when you have something like stragglers to think about asynchronously sharing that information. So from a communication efficiency point of view, I think it makes a lot more sense to perform asynchronous computation. The way that we sort of got around this and the way that we think about this in some of the methods we've developed is that we deliver synchronous model updates, but we allow for variable amounts of work to be done. So this is kind of in between these two approaches. So if you have a device that's, it's a straggler, it's performing a very little amount of local computation, you can still send whatever computation is done at the end of some time window. So it's still a synchronous update, but it could be that the updates that you're getting from different devices look different, right? Because some of the devices are able to perform more computation than others. And this kind of goes, it actually lends itself to some of the analyses that are already being done on statistical heterogeneity, kind of just amplifies some of those issues.
I see. That makes sense. Well, I guess if you're going to vary the amount of work each client is being done, you'd imagine also you want those clients to consider how useful those pieces of information they're going to crank on are. Mm-hmm. So if they've got, and making a good decision about that, it probably have a big influence on the outcome.
Yeah, I think this question also, I think an important question here is how this all relates to issues of bias. One of the reasons that a device might be straggling is it could be an older device or a device that has poor network connection, and I think there are obvious concerns there about how we try to fairly treat those devices as part of this process.
Sure. Well, one final question. The person's writing, do you think there could be new types of model architectures out there that are more suitable for FL? So for example, he or she mentions model architectures purposely designed to then be aggregated later. So do you feel that maybe there might be some part of the design space where you could have architectures that have been designed on first principles to know they're going to be aggregated later and how that might affect, or something related to this idea?
Yeah, that's a super interesting question. So I'll say at a high level, I think absolutely optimization and training is highly related to modeling. I think that's one of the things we've really been realizing in our own research. In fact, there's been some interesting recent work in looking at some of the a very simplified form of one of the multitask learning objectives that I presented, where you're basically looking at a mean regularized objective. And in learning this model or this architecture via this mean regularized objective, you can actually provably show that methods like federated averaging can converge and can converge more quickly than other baselines. So I think there's a really tight link here between the objective that you're solving, the model that you're solving, and the optimization method that you're using. And yeah, I think it's a good question. I think there's a lot more work to be done to understand the effects of modeling on other aspects of the pipeline.
Cool. Well, with that, I want to thank you again for this brilliant talk, and it's stimulated so much conversation in the audience. And so thank you much again for spending the time with us.
Yeah, thanks for having me. Thanks, everyone.
Great.